Hello and welcome to this lecture on ultrasound image quality metrics. I am Professor Himanshu Shekhar. So today let's discuss about the quality of ultrasound images. So how would I know if an ultrasound image is good? We would definitely need some metrics, right? So some of the metrics are spatial resolution, contrast resolution, signal to noise ratio, presence or absence of artifacts, and the overall diagnostic usefulness of an image. What is spatial resolution? I believe you're already quite familiar with the concept of spatial resolution, or at least the resolution of an image. When you capture an image using your camera, if you get a sharp image, that image has good resolution. If the image is in focus, then you get good resolution. However, if let's say you move the camera while taking the image gets blurry and the resolution gets degraded. So that is what spatial resolution is all about. Then comes the contrast resolution or the contrast. I think you are familiar with the fact that if you wear a white dress and let's say stand next to a white wall, when you take a picture, you will not get very good contrast in the image. Now, there might be enough light, there might be enough signal, however, there will be poor contrast, which will reduce the ability to visualize you against the wall. And that is why contrast is also an important parameter when we assess the quality of an image. Next comes the signal to noise ratio. So let us say you take your camera image in the late evening when there is not adequate light. You will see that there is a grainy structure present, which is because of noise in your image. There is not enough signal relative to the background noise which is generated by your electronics and sensors, and therefore the signal to noise ratio of the image is poor. So signal to noise ratio is another important parameter which is used to assess the quality of an image. Next come artifacts. Artifacts refer to structures present in the image which should not be there. So essentially they are like fake targets which should not be there in an image. And the presence or absence of artifacts can mean a lot of things in ultrasound. Therefore, we will dedicate an entire lecture to artifacts, and we will not discuss artifacts in detail in the present lecture. And lastly, the overall diagnostic usefulness. This is something that can be assessed by trained sonographers and radiologists. So let us say you have an image with good spatial resolution, good contrast resolution, high signal to noise ratio, no artifacts per se, but it is still possible that the diagnostic information that the clinician or the radiologist is looking for is not present in the image. Let's say you are trying to visualize the tumor, but it is not possible using an ultrasound image for a variety of reasons. Perhaps the acoustic properties of the tumor are very similar to the background. So that is where the concept of diagnostic usefulness comes through. We will discuss it in more detail in later lectures. Next, let us discuss the transducer bandwidth. So how would I know what is the bandwidth of transducer? The bandwidth actually determines the range of frequencies in which the transducer can operate. So consider this water immersion setup which we have discussed previously in the context of field measurements. Here, let us say I put a transducer in immersion and excite it with an impulse signal, which could be a spike voltage with positive or negative polarity. And then I place the hydrophone at the focus or any other spatially relevant point where I am interested in making the measurement. Then I acquire the signal and capture it using a digital oscilloscope and visualize the signal. So here is a simulated signal that I have created. This signal looks like an enveloped sinusoid, something like a Gaussian envelope sinusoid. And this shows how the transducer will ring in response to the impulse. And therefore, this is the impulse response of the transducer. If you take the Fourier transform of this signal, what you get is a frequency response, which tells you the center frequency of the transducer, and you can also calculate the 3 dB or the 6 dB bandwidth, which is the range of frequencies over which this transducer can operate. So the wider the bandwidth, better the transducer and better the imaging performance, as we will see later. So next, let's discuss about the beam pattern of a single element transducer and how this influences image quality. So to get the beam pattern of let's say a disc transducer or a rectangular transducer, which is a planar object, you would have to start with a mathematical formulation called the spatial diffraction integral formulation, and then you could make several approximations to arrive with what we call Fresnel approximation and Fraunhofer approximation. And essentially what we are doing is we are considering our extended source, our transducer, to be a combination of a large number of infinitesimal objects or points, and we just sum up the signal from those points to get the beam profile. So this is a very approximate solution where we get two distinct zones where there is a qualitative and quantitative change in the field profile. And the first zone, which is also called the near field, which is closest to the transducer, is called the Fresnel zone or the near field. In the Fresnel zone, the beam width or the width of the beam can be approximated to be the same as the diameter of my crystal. So this is my Fresnel zone or the near field. And then you have the focal point, which is the end of the Fresnel zone. And after that, the beam starts diverging. And this zone is now called the Fraunhofer zone. So this is also known as far field. In the far field, the beam width changes with the axial distance z. So as you move further and further away, the beam width increases, as can be seen by this formula, beam width equal to lambda z by d, d being the diameter of the transducer. So now, if we consider this transducer as an object and I look at the beam is not just like a single ray of light, but the beam is a three-dimensional feature. So here you can see the shape of the beam from this rectangular transducer. It has an axial direction, which you can see here, z represents the axial direction. There's a lateral direction, which is perpendicular to the axial direction, and another perpendicular direction, which is the elevational direction. So all these planes contribute to the signal. Now, here is a simulation of an ultrasound beam. So you can see there are a lot of variations in the near field and not so much in the far field, but the beam starts diverging in the far field. But again, as an approximation, this two regime model is pretty reasonable, where we consider a Fresnel zone and a Fraunhofer zone. Now, if I take a cut, an axial cut through this beam profile, what I will see that there are large number of maxima and minima in the near field, and then after the last axial maxima, the ultrasound pressure starts dropping, and that is because of beam divergence and diffraction. And this on-axis beam profile tells us that the focal point of this transducer is about 0.05 centimeters. Next, let's discuss the spatial resolution of my imaging system. My imaging system ought to have good spatial resolution so that the images will appear sharp. Now, as I said, the spatial resolution refers to the ability to differentiate structures located close by in space in my image. There's a quantity called the point spread function, which is a metric that is analyzed to determine image quality of an imaging system. What is a point spread function? Literally, point spread function tells you if there's an actual point in the image, how it will be blurred out by the imaging system. Now, if we had a perfect imaging system, all points, however small, would be rendered very sharply in the actual image. But that is not so. Any object which is sub-wavelength can be considered a point object, even though a point object cannot be theoretically realized in practice because a point has zero area. We can consider sub-wavelength objects as points. Now, if the object is larger than the wavelength, considerably larger than the wavelength, typically it is rendered well with the adequate size in the image. However, if the object is sub-wavelength, it will get significantly blurred. So here is an example of a point spread function of a hypothetical imaging system in which this blur actually represents how a point will be depicted in an image. And here is the actual object profile, where there is a very small point and there is a slightly more extended object. And then if you want to model how the image will look like, then what we can do is we take the object and, assuming linear shift invariant systems and a convolution framework, we can convolve the object profile with the point spread function which is shown here to get the image. And you see some blurring is introduced into the image. There are still two objects visible in the image, but the blur is introduced because of the point spread function of the object, of the imaging system. Now, It turns out for modalities such as microscopy, optical microscopy, the point spread function does not have an angular dependence, it is isotropic. But for ultrasound, the point spread function is anisotropic. And here is an example of the point spread function of an ultrasound transducer, which was assessed by imaging wire targets. So there are two wire targets at different depths, and as you can see, the point spread function is actually spatially dependent in this case. It's not exactly the same, and it's blurred out in a certain way. But you can also see that in the axial direction, the blur is not so strong, and in the lateral direction here, it blurs it out, stretches it out more. So this is because the point spread function of an ultrasound image is anisotropic. Now let us discuss in more detail about the axial resolution, lateral resolution, and the elevational resolution. So the axial resolution is a measure of how close two reflectors can be along the axis of the transducer or the ultrasound beam and still be resolved as a separate reflector. So here is a schematic with a transducer, and this is a beam pattern, and along the axial depth there are two objects that are located. Can we always separate these two objects in images? Not necessarily. This depends on the pulse length of the ultrasound used to form these images. Now, if the pulse length is very short, imagine in an ideal scenario, if the pulse is like an impulse with no width, then there will be very clear, distinct echoes coming from these two scatterers. However, if the pulse is an extended pulse, for example, consider a 4 or 5 cycle sinusoidal burst. Now, what would happen is as these objects start coming closer and closer, when I fire a pulse with a finite spatial pulse length, then the echoes from these two targets will start overlapping together, and there may be ambiguity on whether or not these two targets can be resolved. And therefore, it is important to image with a short pulse length if we want to get good axial resolution. So, like I said, impulse excitation can be used. In some cases, it is not practical. Then a very short sine burst can be used to excite the transducer to get good axial resolution. And like I said earlier, if the transducer is damped, it will not ring a lot. If it doesn't ring a lot, then the spatial pulse length will be shorter and the axial resolution will be better. Now, even if we excite the transducer using an impulse, it turns out that the pulse that is generated, as I showed you earlier in the impulse response measurement, is sinusoidal in nature, and this is because of the band pass response of the transducer. Your transducer is actually working like a filter, and even if you excite it using an impulse, it will actually generate the frequencies which are within its bandwidth, and that would look like a modulated sine burst. So the axial resolution can actually be calculated as lambda times n by 2, where n is the number of cycles in the pulse, or c times delta t by 2, where delta t is the temporal pulse length. Next, let's discuss the lateral resolution. So like I mentioned, the lateral resolution is spatially dependent for a transducer beam, and the lateral resolution tells you whether or not you can differentiate two structures which are located apart laterally within the ultrasound beam. So now the lateral resolution is given by lambda z by d. We saw this formula earlier as the beam width in the far field, right? So assuming that imaging is done in the far field, the beam width actually tells you the lateral resolution. Why is that? Well, consider two scatterers that are located within a beam. So now in our imaging, we do not assume a beam as an extended object, but we think of it as a ray. So anything which is located within the beam, there's ambiguity on whether the scatter is coming from a single scatterer or from multiple scatterers. And by default, we will not be able to differentiate between these two scatterers. On the other hand, if the scatterers, one is located within a beam and the other is located outside the beam, we will easily be able to differentiate them, and therefore the lateral resolution or the minimum distance between these two scatterers here, which can be differentiated by our imaging system, will be dictated by the beam width, which is lambda z by d. Now the best lateral resolution, as you would have guessed, will be obtained at the focus because the beam width is the most narrow at the focus. And here is a focus transducer with a narrow beam width at the focus. This is an unfocused transducer. You do get some natural focusing here because of the aperture and the geometry of the transducer, but still the focal width is relatively wide, so you will not get a very sharp image using this. And here are images of point scatterers located in the beam. So you can see that the point is not blurred a lot here, but it does get spread a lot along the lateral direction here and here. So essentially at the focus you have excellent lateral resolution, but as you move away from the focus you have poor lateral resolution. Next comes the elevational resolution, which is the ability to differentiate two structures located apart in the elevational plane. So it is important to remember that when we are sending an ultrasound beam, it is not like a planar beam, but it has a finite thickness in the elevational direction as well. So the beam width in the elevational direction will also determine the quality of the image. Any structures which are within the beam in the elevational direction will contribute to the image. And therefore, a lens can be used to improve the elevational resolution. But the challenge is a single lens has a fixed focus, so the elevational resolution can be good at a given point at the elevational focus, but it will degrade at other points. And that is where electronic arrays are created, such as 1.5 dimensional arrays, which we will discuss in more detail in the beam forming chapter. And there can be electronic focusing in the elevational plane, and we can vary the depth at which we can do the focusing, and we can maintain consistent imaging quality at different depths with respect to elevational resolution. Next, let's discuss signal to noise ratio. Signal to noise ratio is a very popular metric, and for ultrasound we can calculate the signal to noise ratio in this manner. Imagine you have a structure where you have a cyst and you have a targeted region, which could be a tumor, for example. Now in the cyst it is fluid filled, so you wouldn't really be getting much signal from the cyst. Essentially we can make an assumption that whatever signal we are getting from the cyst is actually noise, which is coming from the thermal noise of your transducer electronics, etc. Now if I look at the variance of the signal from the cyst, this represents the variation of noise, and if I look at the signal from the object, this is the signal. So this ratio is called the signal to noise ratio. Now how do I improve my signal to noise ratio? If I use highly sensitive crystals, high quality piezoelectric materials, then the crystals are more sensitive and then the signal strength will be more relative to the noise. I would also have to have proper shielding of my probe so that there is no RF noise, and that will improve the signal to noise ratio. Further, once I capture the signal using my ultrasound transducer, it will be very weak. So I have to amplify it to a certain level, which is done using a low noise preamplifier. The design of the preamplifier will affect the imaging quality. And also if I transmit higher energy, of course within safety limits, because we cannot exceed the safety limits as we will learn in another chapter, then we get better signal to noise ratio. There are also a few other aspects. For example, when you are digitizing your signal, you are converting your analog signal to the digital signal. The higher number of bits that you use, the better your signal to noise ratio will be. Further, we can exploit spatial filtering approaches or beam forming, again to be discussed in a subsequent chapter, that helps improve the signal to noise ratio. We can take images and either we can average in along the time direction, or we can perform some spatial averaging, which is called compounding, and this will also improve my signal to noise ratio. I could perform some post processing for noise reduction, for denoising. I can use adaptive filters. For example, I could use a Wiener filter, or I could use wavelet denoising, and these kind of post processing can be used to reduce the noise and improve the signal to noise ratio. Lastly, there are speckle reduction algorithms. So speckle, it's not exactly random like noise, it is deterministic. It is caused by constructive and destructive interference of scatterers which are sub-wavelength. But In some mathematical formulations, speckle can be modeled as a multiplicative noise. Instead of noise that gets added to the signal, speckle is modeled as noise that gets multiplied to the signal. So if we reduce speckle by some speckle reduction algorithms, a large number of algorithms exist, then we can improve the signal to noise ratio. Next, let's discuss the topic of contrast resolution. So contrast resolution refers to the ability to differentiate two scatterers that differ in intensity. And again, using this type of formulation, contrast can be calculated in decibels using 20 log 10 of the signal in the region of interest by the signal in the background. So contrast to noise ratio is another parameter where we take the difference of the signal and divide by the square root of their variance. This tells us these are standard deviation squares, by the way, so they are variances. So this tells you about the contrast relative to the noise. Now, as I had said before, that the beam width determines the lateral resolution. So if I take a cross section of a beam, the main lobe width, right? The width of the main lobe actually determines the lateral resolution. Now, a typical ultrasound beam will also have side lobes, okay? And I did not show that in the initial Fresnel-Fraunhofer simplification, but a beam also has side lobes. So now, these side lobes can cause trouble. For example, here is the image of a bubble cloud. Bubbles are strong scatterers of ultrasound, so you can think of this as a strong target. Now these bubbles are in a tube, so if we take a cross section, it will look like a circle. But what are these structures? They seem to be spread out. It seems as if the cloud is taken and smeared laterally. And this is actually because of the side lobes. The side lobes are taking the energy from the center of the cloud and redistributing it towards the side. So this is certainly not good for our contrast. So the side lobe level, how strong the side lobe is relative to the main lobe, actually dictates the contrast resolution. And in this case, let's assume the side lobe is down by about 15 decibels. So the contrast resolution will be about 15 decibels. This is because as you go lower than 15 decibels, the side lobes will start contributing to the background signal and not the main lobe. Now to improve the contrast, you can compress the dynamic range by logarithmic compression. We will discuss this more in the image reconstruction chapter. And if you compress the dynamic range, you will highlight some of the weaker scatterers that were not previously visible, and therefore the contrast resolution will improve. The presence of speckle also degrades contrast, so if we apply some algorithms which will reduce speckle, then you will get better contrast resolution. Further, if we have higher dynamic range, if we capture higher dynamic range, then it improves contrast. So for example, if your transducer has a dynamic range of say 40 dB versus 60 dB, in case of 60 dB, you will get better contrast. And there are also a set of drugs essentially. Yes, they are classified as drugs, but they are actually microbubbles, stabilized microbubbles, which are smaller than the size of red blood cells. They are used as ultrasound contrast agents to improve contrast from vascular organs, blood-filled organs such as heart, blood vessels, arteries, veins, etc. So we can also administer these contrast agents into the human body to improve contrast where there is none or poor contrast, and this will be discussed in a subsequent chapter. Now, in terms of quality assurance for my system, I can do a few things. For example, we can get a system calibrated consistently to make sure that the outputs that are coming out of the system are consistent, to make sure that if we have transducer arrays, none of the transducer elements are low in sensitivity relative to the other elements. And for doing this, we can again use an immersion setup. Using a hydrophone, we can scan the beam, we can measure the acoustic outputs, get a 3D map of the beam profile, etc. And here is some pictures from our lab where you have some single element transducers, and then this is a needle hydrophone. So you put this in the field and you measure the field, and this is one way of quality assurance. Another way of quality assurance is using standard phantoms. So this is a commercial phantom that is present in our lab, and this phantom has a set of you would say prior known targets. So these targets are point targets. There are also some hyperechoic targets which are more scattering than the background. There are some hypoechoic targets which are like cysts. Like cysts in the body are fluid filled and they are hypoechoic. And then we can look at the imaging performance by looking at the image. So for example, see here, as we go deeper and deeper, it seems that the points that are being imaged, so these are all points by the way, but they look like rice grain structures, and that is because of the anisotropic point spread function of ultrasound. So there is some spatial variation. Also, you can look at the cysts from which you can determine the contrast, signal to noise ratio, etc. So by having such structures where we already know what to expect in ultrasound images, we can actually perform quality assurance. In case a transducer element is dead, for example, if we have some damage to the transducer array, typically you see streaks in the phantom images and you would know for sure that there is some damage to the array. So in this manner, we are able to perform quality assurance and you are also able to take these points, we measure the widths, we can get the point spread function of the ultrasound imaging system, and as I said, the point spread function in general will be depth dependent or spatially dependent, and then you can determine the point spread function. From the point spread function, you can calculate the main lobe width, the axial width, the lateral width. Also, you can measure the side lobe level. That will tell you a lot of things about the imaging system. To summarize, in this lecture, we discussed a variety of topics. We discussed the spatial resolution, the axial, lateral, and elevational resolution. Typically, in introductory courses, people restrict to axial and lateral resolution only, but elevational resolution is also important and it dictates imaging quality. We discussed point spread function in ultrasound. We discussed the ultrasound beam profile, including near field and far field approximations, simplifications which help us understand in a simple way the beam profile. We also discussed image quality metrics, including resolution, contrast, signal to noise ratio. The topic of artifacts will be for a subsequent lecture. And we lastly discuss the use of phantoms for quality assurance. So I hope you found this lecture interesting. I'll see you in the next lecture. Thank you.